Wearable sensors are becoming increasingly prominent in rehabilitation research. However, the majority of clinical studies that use them don't actually extract kinematic movements, but rather take the raw sensor data and pass those through machine learning algorithms to produce clinical measures. And this is in part because extracting kinematics from the sensor data is particularly challenging. Two of the hard challenges are first, calibrating the sensor position on the body, and then second, fusing the data from multiple sensors in order to understand what the person is doing in 3 dimensions. However, rapid advances in markerless pose estimation provide a complementary approach that can really help with this problem. And first, I want to talk about a sensor platform I've been developing in collaboration with the Rogers Lab that is a flexible wearable sensor that has EMG electrodes on the back, and when you stick it to the skin, it records the muscle activity as well as the movement. And then using fairly standard algorithms like a complementary filter, we can take that raw sensor data and fuse that into a 3-dimensional orientation estimate that's fairly robust and drift-free. And on the right, you can see an example of this where I am showing the output from a smartphone, the app that's collecting that data and visualizing it in real time in comparison to Vicon tracking, where you can see a pretty nice correspondence. And then that's the orientation of the individual sensors. But if we want to actually measure something like the knee angle, it's fairly straightforward for a joint with only 1 degree of freedom to place a sensor on either side of the joint, and then from the statistical properties of that data to actually estimate the joint axis and then measure the movement. And so that's what I'm showing on the right. And there's a number of traces showing the angles from the different body parts, but for example, if you look in the middle plot, the knee angle, the solid line is from the IMU and the dashed line is from the video-based estimation, and they generally show a fairly good correspondence. There's actually points where the video has a great error and drops out and shows more error. And then at the bottom, you can also see examples of the electromyography captured by this system. But this approach doesn't really scale to tracking things like the shoulder with multiple degrees of freedom. And for this, we need a better 3-dimensional understanding of the person in order to calibrate and understand how that relates to the body movements. And I wish I had time to go through a review that does justice to the body of literature in this field, but just to highlight a few points around markerless pose estimation. Approaches that do 2D joint localizations are becoming fairly robust, such as open pose or its successor alpha pose, or deep lab cut if you're training on markers that are outside of the standard data sets. And there also are approaches that can take these 2-dimensional joints and project them into a 3-dimensional set of joint locations. But I'm particularly interested in approaches that solve the inverse kinematic problem and understand the body pose that gave rise to those observations. One great example of this is human mesh recovery. And these algorithms will take an image and directly regress it to a set of pose parameters. And a common model describing the pose is the SMPL model. And this originated for computer graphics. And while it's very powerful, one limitation is it doesn't actually give a representation that corresponds to the standard biomechanical deconstruction, such as elbow flexion or shoulder elevation or the plane that the shoulder's elevating in. And then finally, there's work in doing video and sensor fusion, and including the work of Malison that does this in the wild. One key difference with my work is that we extract the actual joint angles from that data, and in addition show that using this calibration, we can continue to track a subset of the joints only using the sensor fusion. And so the methodology used here is, first I took a stereo video of a rehabilitation participant and then passed it through 2 parallel pipelines. The first is open pose, which perform joint localization on each frame for each image independently. And then human mesh recovery would take the images and also come up with a 3-dimensional pose estimate. And then I passed it through a trajectory optimization that includes some kinematic constraints and some temporal smoothing where, like similar to the bundle adjustment used in Arnaud et al. In 2019. And then finally ran it through a biomechanical decomposition to extract the actual joint movements. So going through each of those steps in a touch more detail. So here is a sample of the video from open pose, and this is a fairly standard thing to do. You can see there's some high frequency jitter there that's not realistic. This is partly because it processes each frame independently. And while I was collecting the data in stereo and hoped that would be sufficient, trying to directly do the geometric projection and come up with a 3-dimensional pose generates a lot of unusual or unrealistic body postures and abrupt transitions that aren't realistic. And so to partly address that, I used human mesh recovery, and amongst its benefits are the fact it directly goes from images to pose estimate, but also that it's trained with an adversarial prior, which forces it to only produce realistic poses that people can do and not hyperextend elbows and put arms through the body. But one limitation of it is it doesn't always produce a model that, when projected back into the image, produces the best fit to the joints. And so to solve this, as well as calibrate in the positioning of the IMU, I then optimized this function here, and I won't go through it all in detail, but essentially it has a parameter for the smoothness with time, and that's similar to the bundle adjustment I mentioned earlier. And then it adds anatomic constraints, specifically things like not hyperextending joints and constraining joints to only degrees of freedom they have in reality. And then finally it adds constraints on the calibration of the IMU to extract the relative rotation of those joints. And then I mentioned the problems with the number of parameters SMPL has. So it has 72 parameters describing the body pose, and that's a lot more than we would normally use clinically. And also what it defines as 0 is this T posture, but what we often talk about clinically is with the arms down beside their side. And so it wasn't terribly difficult to convert from one to the other, but this is a very important step for using these algorithms clinically and talking to clinicians. And so this is the whole algorithm put together, and you can see the projected image joint locations back into the image are nice and smooth and doesn't have the high frequency jitter they originally had. And then in the lower right in blue you can see the model IMU or joint body segment orientations, and the red is the IMU after correcting for the calibration position, showing a very nice alignment, as well as the fact then below the extracted joint angles. And when we reproject all this data back into the original image and orientation space, we have a fairly low residual error. And then excitingly, we can also use this to optimize for the pose position even when we don't have the video data. And so here I'm showing a segment of arm movements without video during wheelchair propulsion, showing very standard cyclical movements. So just briefly in conclusion and next steps, we've shown that we can obtain biomechanical measures with and without videos, but this work needs more validation on more subjects. It needs ground truth. We need to know how accurate it is, and it particularly needs to be made easier to use, and I'd like to move to a more direct inference approach rather than optimization, which is a little slow. And finally, I'd like to acknowledge all the support that got me here. Thank you very much.